Okay, so hi everyone again. Welcome to our last invited speaker talk of the course. Today we have Ernest Ho. He's an expert consultant for Brown University, working with Wilson Chukolov, and he's been working over a year now on converting this detailed model of epilepsy in a cortical network into NetPyNE. The model is interesting also because it uses RxD, and I'm very happy and very thankful to Ernest for agreeing to give this talk. And please welcome everybody, Ernest Ho. Thanks.
So it's my turn now, right?
Yes.
Okay. So I'm really honored to be invited to present, being the last speaker of this course. So my name is Ernest Ho. Today I'm going to give a talk with the topic conversion of a cortical neuronal network model of epileptic seizure to NetPyNE. So before I start this presentation, I just want to tell you guys the story about this entire presentation. So basically, the story started like a few years ago when I was a postdoc with Wilson Chukolov at Brown University. At that time, my job was to develop a computational model of epilepsy in the cortical area. So the reason why we did that was because we, at that time, were motivated by some of our own clinical data, which suggests that seizure propagation is not a homogeneous event, it's a heterogeneous event, in the sense that in addition to the most common spike wave discharge we see in a lot of patients during seizure, we also see in some patients, we have some higher frequency but lower amplitude oscillations in the EEG while patients are having seizure. So those oscillations are instead of a 3 to 5 hertz, as we saw in a lot of epilepsy patients, these higher frequency, low amplitude oscillations are much of a high frequency, about 50, 60 hertz, and they are of the lower amplitude. And we also have a spiking correlates for both of these phenomena. And what is more interesting was that in some other patients, we see a mixture of these two modes of seizure propagation. So first, when seizure started, initially we saw some high frequency, low amplitude oscillations, but then it gradually gave away to the more regular spike wave discharges. So basically we have in conclusion, for all those patients, we see we have three types of phenomena. One is the more regular spike wave discharges. Second is the higher amplitude, lower frequency oscillations. And in some patients, we see a mixture of these two. So as a modeler, I wanted to understand the biophysical underpinnings of how those three phenomena can arise. So what we did is that we came up with a cortical network model, and then basically by adjusting the parameters, we were able to reproduce and explain how these three types of seizures arises. And of course, at that time, we did our code in C++ and MPI, which was good and which was fast. But then, fast forward to today, we want to repurpose the code for something else. We want to investigate another topic in seizure, and we kind of want to repurpose the code. But the issue is that the code, because it was written in C++, was too long, and it became too clunky because C++ code, while it's fast, is not specifically designed for adding biophysical features to cortical network models. So we were thinking about it, what's the best way to deal with it. So at the end, we come up with a solution with Safa and Wilson that we wanted to use neurons and NetPyNE to convert our model to NetPyNE, so that going forward we can be more efficient in terms of changing biophysical parameters in the computational model. So basically, that's the story of the story of this presentation. And now I'm going to start it. So So in our original model, like which was published in the 2016 in Journal of Computational Neuroscience, so the lab work that like we did before was a individual cortical model of 9 times 9 mini columns. Each column has 16 single compartment neurons, 4 of which were inhibitory interneurons. And like those, they're not that complex, but it's a small-ish model so that we can just show some proof of concept work, like in knowing what are the biophysical parameters underlying all those 3 types of seizure transition. So in addition to neurons, we also have like different different ionic parameters. The most important one being the potassium. So we have like extracellular potassium being regulated by local glial mechanism, and the local glial mechanism is encapsulated by well-defined interstitial space for each neuron. Well, for the details of this mechanism, I refer you to this paper, KJ et al. 2000. It's in Journal of Neurophysiology. And so basically, this is that is a configuration of our old model. So we have like all those mini columns arranged in a line by line manner, and each mini column has like 16 neurons, 4 of which were like the interneurons here. And of course, each neuron is single compartment, which consists of a soma, intracellular space. And we also, in terms of like, I'm just repeating, in terms of like the buffering, we have a smallish interstitial space that encapsulates the soma, and all the bufferings occur in this region. And there's also, like an extracellular space for potassium. So basically, for the intracellular potassium, first, if they want to go out, they have to go to this buffering space where the buffering occurs, and then they will diffuse to the extracellular space. So it's like a 3-layer approach that we were using in this cortical model. That's important because we are going to have more of it later in the presentation. And so there's a summary of the results. So basically, this is a short summary. So basically, like the idea is that by playing with different parameters of this model, we were able to reproduce all the 3 types of seizure propagation that we saw in our clinical data. For example, this one, in a high inhibition scenario, we did see, for example, like here, when the seizure starts, we were able to reproduce, like some gamma phenomena. You can see it, right? It is at around 30-40 hertz. And if you look at the LFP analog, you can see, like all those, lower amplitude, higher frequency oscillations. And there's also, like the spiking correlates. So that is one that's one type of seizure that we one of the 3 types of seizures that we were able to reproduce. And the second type, which were the most common one, is the spike wave discharges. In a more low inhibition environment, we were able to reproduce during seizure a lower frequency by more common spike wave discharges. You can see that in the frequency is much lower. It's about 5 hertz here. So it's 2 seconds. It's about like 5 to 6 hertz, and it's of a much higher amplitude. And also, we were able to reproduce the last one, which is higher frequency gave way to a lower frequency, more regular discharge. So you can see that when the seizure starts, you can have like a bit of a higher frequency, like 20 hertz, like oscillations. Then as the inhibition breaks down, it slowly gives way to a more regular, lower frequency spike wave discharge, as you can see here. So you can see here, like initially when the seizure starts, there's a lot of inhibition. So like the interneurons are firing like crazy, and then since the interneurons are firing crazy, they get into the depressing block. Once the interneurons get into the depressing block, then there was no inhibition, and the pyramidal cells will just automatically getting into a spike wave discharge mode. Okay, so in any case, so that's just a brief summary of the results. And I mean, if you guys want to know more about the results, you can, I'll just refer you to our paper, like that was published in Journal of Neuroscience 2016. And so what conversion? So right now, because we want to repurpose, like this thing for something newer, to investigate more about seizure. So we kind of want to repurpose it. But the problem is that it's just getting too complex, too difficult to repurpose it, because it's written in C++ with MPF of parallel processing. And while they are good, it's just hard to rewrite the code. And the code actually underwent several generations of evolutions, so it's getting really clunky. So there are also maintenance issues and stuff like that. So at the end, we just decided that it was just easier for us to switch to another platform, because we are going to foresee, in the future, we are going to be playing with lots of biophysical features such as multi-compartment models, and maybe different types of synapses and stuff like that. So we definitely are going to need a more versatile platform for this to happen. Otherwise, we're going to spend so much time coding, and we are not going to spend enough time, understanding the biophysical property of the network. So what we did is that, we are starting to slowly convert the code into NetPyNE, and so right now, it's still in progress. But right now we have a very toy model. So it is instead of about 2,000 neurons as in our original cortical model. Now we are able to produce a reduced model of roughly 300 single compartment neurons in our NetPyNE. So, and of these 300 single compartment models, roughly 15% of those are inhibitory cells. And it has a simplified two-layer structure, which is just has a layer 2 and 3 and layer 5. I mean, in the future, we're going to expand it, but now, because we just want to play with NetPyNE, and we kind of want to have a smaller model so that we want to get a hand out of it first. Then once we are more familiar with the platform, we are going to add more complexity to the model. And it's a toy model, and we have all those ionic currents, sodium, potassium, calcium mediated potassium current, and of course there will also be potassium pump currents and lead currents. And we also have the potassium helio buffering. So the ultimate goal is that we are going to have a 6-layer cortex with multi-compartment neurons. But now we are not there yet. So just to compare between the old code and the new NetPyNE code. So that's the old one. We have instead of the 9 times 9 linear structure, we forego this one, and then we are going to have this setup. So you can see all the 300 neurons are here. By the way, in the current NetPyNE setup, you see a 2-dimensional space. It's actually not a 2-dimensional, it's actually 3-dimensional. So what you see is just a projection of the neuronal configuration in this presentation. So it's actually a 3-dimensional, but it's projected to 2-dimensional. So you can see, the layers, there's a layer 2, 3, and there's a layer 5, and all those brownish guys are inhibitory interneurons. The rest are pyramidal cells. And so just want to tell you some major challenges in conversion. So actually, in most cases, the conversion has been pretty smooth. We use the HOC file for individual neuronal properties, but the conversion is mostly smooth. The only challenge that we had was that we had to use the reaction diffusion model for potassium diffusion. Why it was a challenge? It was because we were trying to fit a 3-layer structure to the reaction diffusion model, which actually turns out to be a bit difficult, but we overcome that. So, and in the process of this conversion, in the process of trying to fit a 3-layer potassium model into this reaction diffusion module of neuron, we also discovered several bugs on the RSD model of neurons and NetPyNE, which was good because like there's a mutually beneficial process. And the reason why it's difficult was because like most NetPyNE examples on potassium ileal mechanism had a different structure. I'll show you why it was the case. So I mean, I was looking at like when I was trying to fit the 3-layer model into the resonance diffusion module of neurons, I was looking at examples, and most of the examples that they were provided had only this 2-layer structure, in which there was a soma and there was an intracellular space, and then outside of it was the extracellular space, and all the glial happens in this this entire region, which, well, I mean, that's actually one representation, but that was not the representation that we wanted to use. The representation that we wanted to use was this one, as I showed you before. We had the intracellular space, and then we had the interstitial space, in which the potassium ileal buffering occurs. And then we also have the extracellular space where the buffer potassium diffuses outside. So it turns out that in order to fit this structure into a NetPyNE, it was a challenge, but we were able to overcome it. And then with several strategies, first of all, we had to invent a surrogate ion to make the diffusion to happen. And second, we also have to introduce another module called multi-compartment reactions to handle this 3-layer structure. But eventually, all is well that ends well, except that it took us, like a few months to accomplish this. So basically, I'm going to show you, like some of the preliminary simulations of the NetPyNE model. So that is one of the simulations. You can see that basically, we are pretending to have like a probe that gets into the cortex vertically. So that's a layer by layer, like LFP reading of the simulation. So you can see like spike wave discharges about, like 6 Hertz, 7 Hertz happening. You can see the radius spike wave discharges. So that's one of the simulations. And those basically represent, the readings on different layers. And also, we were able to do potassium diffusion. So that is basically, some results of the that's basically, I'll just show you a visualization of the potassium diffusion happening in that simulation. Of course, there is a 2D projection of a 3D simulation. So you can see that there's a higher potassium concentration at a certain moment, like in the simulation, like 10 micromolar in the like layer 5, but then there's a bit lower in the layer 2, 3 region. So just want to show you, like the capacity of the visualization of NetPyNE. And so basically that is about the end of my presentation. So the take-home message is that, for me, in order for me to overcome the challenge, I had to be in constant interaction with the NetPyNE and the neuron team. And I think, if you have something new, if you want to add features, if you have something new to add to your model, it's very important to talk with the NetPyNE and neuron team, because, talking with them, will enable both of the team members and yourself to learn more about the features and to learn more about the software. And also, if something you feel is not right, chances are you find a bug. I think it's actually good because it's a mutually beneficial process. Let them know about like the bug that you may have discovered, and they are very good at telling you that whether it's a bug or not. If it's a bug, they are really, really fast in fixing it. So the possible next step is that we are actually trying to use this going forward. We are actually trying to use this NetPyNE model to investigate some animal models of epilepsy, such as 4AP and low MG 2+ scenarios. So basically, that's it. And I hope you enjoyed the presentation.
Great. Thank you so much, Ernest. That was fantastic.
Yeah. Okay,
really useful.
Great. So Is there any question?
And thank you so much for helping us fix all these bugs and improving the package. We're very helpful as well. Very
Okay, great. I mean,
thankful,
I look forward to communicating with you in the future, like in terms of like expanding this model.
Yes, of course. And let's see if there's any questions from the students or anyone.
Hello, I have a question.
Hi. Yes.
I was interested in the way you modeled the diffusion from the potassium in the extracellular space, because as far as I understood, you defined a reaction, a multi-compartmental reaction. Am I wrong?
Mm-hmm. Well, yes, because we had to use a multi-compartment reaction in order to facilitate this three-layer model.
Okay.
Yeah,
okay, perfect.
And in addition to this, we had to introduce a surrogate ion, a thick ion, to facilitate the exchange of ions in the interstitial layer.
Okay, and didn't you need any like pump to help you to I don't know, the diffusion of the ion in the extracellular space? I mean, I'm just asking because I have a little bit of experience in neuron RxD, and all the examples that I've seen so far use a pump to, you know, push the ions on the space.
No, I mean the pump happens here. I mean between the intracellular and the interstitial space, like there's a potassium pump. I mean this pump is from the neuron itself. You see, can you see my?
Yeah,
arrow?
I can see.
Can you see my mouse?
Yes.
But here is all diffusion.
Okay, I understand.
Yeah, but here, you know, we have pumps.
Okay, perfect. I understand. Yeah. Thanks.
Yeah.
Okay, thanks. Any other questions? Okay, so let's thank our speaker again. Thank you so much, Ernest.
Thank you.
And we'll stay in contact.
Okay, so I'm going to hang up right now, okay?
Okay, thanks.
Okay,
bye.
Bye-bye.
That was really good.
Thank you.
Thank you for the presentation.
Thank you.
Bye.